Good morning, this is Dr. Rajesh Yadav. Today I will discuss about Michaelis mental equation. So today we'll discuss about these equations along with this line-Weaver equation, and we compare of both equations. So this is the reaction in which enzyme is reacting with the substrate and forming enzyme substrate complex. And finally enzyme substrate complex break down into enzyme and product. So graph is showing in the initial velocity V0 or V0 and substrate concentration is S. So as the time going, the velocity will be increased, and after some time the velocity will be maximum. And after that time the velocity will not increase because the amount of substrate will be finished. In the right panel I have shown the beta galactoside is substrate and enzyme is beta galactosidase. So this is the hydrolysis reaction in which beta galactosidase cause hydrolysis of beta galactoside into galactose and ROH group will be released. So this is the example of the enzyme, how the enzyme will work. So when the enzyme will work, it will enhance the rate of reaction, and within the minutes or within the seconds the reaction will be complete. This is the Michaelis mental equation, V0 equal to Vmax S upon Km plus S. If substrate concentration is negligible, then we can negligible here, and then V0 equal to Vmax S upon Km. If we plot the graph between V0 and substrate, this curve will be obtained. So in this Michaelis mental equation, if the value of Km is negligible or substrate concentration is high, then what will be happen? Then V0 or V0 is equal to Vmax S upon S. So S will neutralize. So finally Vmax V0 equal to Vmax. So that means if substrate concentration is very high, the initial velocity is equal to the maximum velocity. In the another situation, if V0 equal to Vmax S upon Km plus S, or if the value of Km is equal to substrate concentration, that means S is equal to Km, then if we put the value of substance, then V0 equal to Vmax upon 2. In another situation, Michaelis mental equation, when substrate concentration is very high, so in that condition Km is negligible and V0 equal to Vmax S upon S. So S will cut from the above S, so V0 equal to Vmax, that we have already studied. Now here in the equation it is shown that enzyme plus substrate form enzyme substrate complex. The rate of the reaction we can calculate, and enzyme substrate further break down into the product and enzyme. So the constant is K1 for the forward reaction while K minus 1 for the reverse reaction. So enzyme substrate either go in the forward direction and form product plus enzyme, or reverse reaction give enzyme plus substrate. So if we calculate the rate of the reaction for the forward reaction, so V1 is proportional to the concentration of the substrate, and concentration of the substrate is E, enzyme and substrate. So if we remove the proportional, the constant is K1. So V1 equal to K1 E and S. Now enzyme substrate complex degradation. If degradation of enzyme substrate complex, so rate of the reaction V2 is proportional to the concentration of enzyme substrate ES plus proportional to the, because ES may be from product or may be from the enzyme. If it is from product, then it is proportional to the ES concentration. So total V2 equal to K minus 1 ES plus K2 ES. If we common here K minus 1 plus K2, so V2 equal to ES k minus 1 plus k2. In the steady state, v1 is equal to v2, so we can put the value of v1 and v2, and we find here k1 es equal to es k minus 1 plus k2. If we calculate that k minus 1 plus k2 upon k1, then we obtain km, and km is equal to enzyme concentration, substrate concentration, oblique and enzyme substrate. So by the equation, we can find out the high Km show the low substrate affinity, while the low Km give information about high substrate affinity. So Km give the information how the enzyme will react with the substrate, either it have high affinity with the substrate or low affinity with the substrate. Now we will study about the Lineweaver-Burke equation. So we can derive Lineweaver-Burke equation for the Michaelis-Menten equation. So according to the Michaelis-Menten equation, V naught equal to Vmax S upon Km plus S. So if we modify here, 1 upon V naught equal to Km plus S upon Vmax S. 1 upon V naught is equal to Km upon Vmax S plus S upon Vmax S. So we can cancel S to S. Then we will find 1 upon V naught equal to Km upon Vmax, 1 upon S plus 1 upon Vmax. So this is the Lineweaver-Burke equation. So we can compare this equation equal to line equation, that's y equal to mx plus c, or here y equal to mx plus b. So we can plot the graph here on the y-axis 1 upon v naught, while on the x-axis 1 upon s. So the slope will define slope equal to km upon vmax, and the intercept is 1 upon vmax. So this is the Lineweaver equation. So the graph we can also plot through this Lineweaver equation. So 1 upon v naught equal to km upon vmax, 1 upon s plus 1 upon vmax. So 1 upon vmax is showing in the graph here, and slope or tan theta is equal to km upon vmax. In the Lineweaver equation, if 1 upon s equal to 0, then 1 upon v naught equal to 1 upon vmax. So graph will be same here. And another modification, if suppose 1 upon v naught equal to 0, then what will be happen? If 1 upon v naught equal to 0, then km upon vmax s equal to minus 1 upon vmax. So km upon s equal to minus 1, and 1 upon s equal to minus k 1 upon km. So minus 1 upon km is shown in the graph here. This is the intercept, and slope equal to km upon vmax. So we can compare here Michaelis-Menten equation with the Lineweaver equation. There is a more probability of error in the Michaelis-Menten equation, while there is a less probability of the error in the Lineweaver equation. So in this way, Lineweaver equation is more precise in compared to the Michaelis-Menten equation. Thank you.